In this video, we want to look at the concept of the derivative and take the derivative of some different functions. So let's go back to the first example we looked at in this chapter. We said, suppose y is some function of x. It depends on x in some way, and in particular, it's equal to 4x squared. Just one point I do want to make. Many times by tradition, we use the letter f to represent a function. But we don't have to use that letter f. We could say y is equal to g of x or h of x or whatever, but we still read it the same way. Y is a function of x. In some cases, we may just repeat the letter y equal y of x, but again, we read it the same way. Y is a function of x, y depends upon x in some way. Well, let's go back to this function, our original function, y is equal to 4x squared. And we looked at the difference quotient for this function. We looked at delta y over delta x. And then we looked at the limit of this difference quotient as delta x approached 0. And we were able to show that we could get the following result. The limit of delta y over delta x, as delta x gets very, very small, it approaches 0, was equal to 8x for our particular function y equal 4x squared. Now this concept, this limit of the difference quotient as delta x approaches 0, is defined to be the derivative of our function or the derivative of y with respect to x. And the symbol we use for that is just dy dx, or another symbol is f prime, the change in the value of the function, the change in y when x increases by 1 unit. And we know that this derivative is itself a function of x. So f prime is a function of x. Now let's go back and look at the graphical interpretation of this derivative. Well, first of all, let's go back and graph out our original function, y equal 4x squared, which graphs out as a parabola. And it's going to look something like this. Here's our x-axis, here's our y-axis. And it's going to be some type of parabola that looks something like this. Y equals some function of x, which is equal to 4x squared. Now, what is the graphical interpretation of the derivative of this function, dy dx or f prime of x? Well, we know that f prime of x for our given function is equal to 8x. We proved that. So we could say, what is the value of our derivative, or what is f prime evaluated at x equal 1? Well, it's just 8 times put in here x equal 1, and that's equal to 8. So what does that tell us? It says when x is equal to 1, somewhere right around here, the slope of the function, the slope of our parabola, is equal to 8, which occurs at point A on our function. The derivative of the function is the same thing as the slope of the function at a given point on the function associated with a given value of x. What if we were to look at the derivative of our function, y equal 4x squared, which is represented by f prime of x, when x takes on the value 2. So now we're looking at f prime, the value of our derivative of this function when x is equal to 2. So remember, f prime is equal to 8x, so just put in there x equals 2, and that comes out to be 16. So what is the graphical interpretation of that number 16? Well, when x is equal to 2, say that's somewhere right around here, the slope of our function, the slope of our parabola, at point B on the function associated with x equals 2 is 16. And that, of course, makes sense that the slope is getting larger from point A to point B. Next question is this. What is the derivative of this function, f prime, evaluated at x equal negative 1? Well, if x is equal to negative 1, f prime of negative 1 would be 8 times minus 1 or minus 8. So we know the slope of our function, the slope of our parabola, is minus 8 at this point right here on the function when x is equal to minus 1. Okay, let's look at a few examples of taking derivatives. Going back to our rules of derivatives, we already showed that when y is a function of x, which is equal to 4x squared, the derivative of our function, dy dx, was 8x. And one way to get that answer, a shortcut way of getting it, is to take the exponent of x, multiply it by the coefficient of x, and then rewrite x and reduce the exponent of x by 1. So we go 2 times 4 is 8, times x, reduce the exponent of x, which is 2, by 1, so 2 minus 1 is 1. It's just 8 times x to the first power, or 8x. So let's give another example. What if I said y is some function of x, which is equal to minus 3 times x to the minus 4 power? What would be dy dx, or f prime of x, for this particular function? Again, using this power function rule for taking derivatives, it's just the exponent of x minus 4 times the coefficient of x. So it's minus 4 times the minus 3, which is plus 12. Rewrite the x, and now reduce the exponent by 1. So it's minus 4, minus 1, or minus 5. Let me give you a couple more examples of taking derivatives. Let's look at the product rule. Suppose we say y depends upon x, and it's equal to one function of x, maybe x squared plus x minus 5, times another function of x, which is maybe x cubed minus 3. And we need to find the derivative of y with respect to x. How do we do it? Well, using the product rule, it's the first times the derivative of the second plus the second times the derivative of the first. So just rewrite the first, x squared plus x minus 5, times the derivative of the second. What's the derivative of the second function with respect to x? 3 times x raised to the second power. So it's just 3x squared. Minus the derivative of 3 with respect to x. Well, that value of y, 3, which is a constant, 3 doesn't change as x changes. So that portion of y doesn't change, or as x changes, so that derivative would be 0. So it's just 3x squared. Plus the second times the derivative of the first function with respect to x, which would be 2x plus 1. And that's all there is to it. One more example I want to give you is how the quotient rule works in taking derivatives. So suppose y is equal to x squared plus x minus 2 all over x cubed plus 8. How would we find the derivative of y with respect to x in this case? Well, the rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So it's the denominator times the derivative of the numerator, which would be 2x plus 1, minus the numerator, which is x squared plus x minus 2, times the derivative of the denominator with respect to x, which is just 3x squared, all over the denominator squared, which would just be x cubed plus 8 squared. And don't worry about simplifying that expression.